Yeah, I'm a mechatronic design engineer. For the past 2 years, I've been working in the robot learning lab with Peter Beal, along with Steven here, with the overarching goal of trying to build low-cost, general-purpose manipulators, and specifically useful. And that's a big topic of what I really wanted to talk about today. So the robot learning lab has a history in trying to get robots to do what we deem useful tasks. And the canonical one for this lab has been robot towel folding, which made it to the highest points of getting made fun of by the United States Congress. So it reached far and wide. These are really challenging tasks, and this has been the robot platform that we've used for a long time. But the PR2 costs $400,000, or rather used to, and is no longer sold because the company no longer exists. And so we really moved forward in thinking, all right, the robot learning lab, there's all this advanced control. Now, what happens if we try and add hardware designers to the mix? What kind of things can we think about when we take a new design approach, really a top-down design approach to make useful robots? So what's useful? That's a word that I'm saying a lot because it's important, especially if you're going to start from top and work down. So the robot must be able to accomplish useful tasks in real-world dynamic environments. So this video actually came out pretty recently, and I love it. And if you're a roboticist, you can ideally see how many takes there are here. Every new camera shot is a different task, and I'm sure is a fully different cut. And these are classic robot videos. It makes it look like robotics has been solved, and it's amazing, and it's awesome, and I found a YouTube video with an underline that said, like, warning, robot is going to take millions of construction jobs tomorrow. And so robotics is solved. That's it. And the reality is, this is only like a year and a half, 2 years ago. And this is what happens when you put robots in an unstructured environment and actually have them and keep them from making all these quick cuts where they're only working. Robots have a very, very challenging time interacting with the real world. Sometimes it's just programming mistakes. Sometimes it's, sand. Sand is hard. And so this follows a lot of reasoning around Sambe Kim, so out of the MIT Cheetah. So he was saying, okay, those robots really have a hard time dealing with these unstructured environments. They specialize in legged locomotion, and they really looked at the problem as we need to fundamentally change how robots are designed and make them able to interact with these unconstrained environments. So this was a full hardware play, a full change in how robots are made. And what I love about this is this doesn't even have vision. This doesn't have motion planning. And so from the ground up, they're able to make these robots that are very resilient to unmodeled environmental interaction. So no vision, they pretty much have no model for their environment. Yet it's still able to move and adapt and interact with an unknown environment. So taking that concept in legged locomotion and applying it to manipulation, it becomes pretty quickly apparent that force control, so having these robots that can interact with an unmodeled environment, is really important for when you want to actually deal with object interaction. So peg and hole is a classic task where if your robot is a millimeter off in its sensing, even if it's a perfectly accurate robot and it doesn't have force control, it'll never be able to feel where that peg is supposed to go. But this robot is the PR2, which has been designed from the ground up to have force control. And it doesn't have the best model of its environment, yet it's still able to just feel that interaction and work to actually make that fit. So if we want robots to accomplish useful tasks in real-world dynamic environments, force control is going to be critical. And the other thing is robots are going to have to provide a reasonable ROI, a return on investment. So going back, all of those, the drywall robot, that thing is at least $1 million. and is going to be for a very long time. And it's going to be hard pressed to say we should use that instead of a human construction worker. So the cost is going to also become a driving factor of accessibility. Otherwise, you're doing cool stuff, but it's not actually going to see the light of day outside of a research lab or a really sweet YouTube video by Boston Dynamics. If cost is a driving factor of accessibility, then it really starts making sense to make cost versus capability, cost versus performance trade-offs. So Toyota has been really invested in making home robotics actually happen. And so they developed the HSR, which is a beautiful use case, case of, all right, we don't need a full, if we want to just declutter a home, we can just get away with a simple 4-degree of freedom elbow arm on a 3DOF Roomba base, and that's enough. If that's what we define as useful, that's enough. And so that really says we can make trade-offs to make robots cheaper. Now, the HSR is actually just their proof of concept of this lower degree of freedom system. They sell it for $10,000, but that's heavily subsidized. And right now, that thing costs at least $60,000 for them to produce. So it's still a proof of concept. It's still in that early stage. And they're trying to ask the question, is this enough? Is this enough for us to do what we want to do? So, and again, if you just want to declutter the floor, the answer is yes, it is. But if you want to start doing more complex tasks, that reduced degree of freedom really starts to minimize what you're actually capable of doing on the types of object interactions that you're capable of. So we added this final constraint, which is if we want robots to accomplish useful tasks in real-world dynamic environments, we don't want to be limited by the capability of the robot. So we really wanted to build what is a human and then build a 7-degree of freedom robot arm where there's 3 in the shoulder, 1 in the elbow, and 3 in the wrist. So we don't want to limit researchers right now, and then ultimately we can bring that back in. So our goal, our project goal going top down has been to build the low-cost manipulation platform for the future of AI-based control, because that's the lab that we're coming from, and that's the driving ideas behind what we're doing. So AI-based control, we really start thinking maybe 0.1 millimeters of repeatability isn't the most important. Maybe if we step back a little bit, if a human can teleoperate the robot and get the robot to do a useful task, then that robot is capable enough. Because we really want to, if we want to minimize cost, we need to make trade-offs. And so that's one of the definitions that we made. And then low cost, we need to make this such that it can actually be scalable and one day see the light of day and actually make enough sense for a consumer to one day be able to afford it. So that brought us to our project goals. We wanted to make a human-sized 7-degree of freedom. That really falls in the anthropomorphic human category. A robot that was compliant and safe with a 2-kilogram payload, because that covers most objects, with a sub $3,000 bill of materials. So this involves trying to open up new design paradigms to actually make that possible. Biggest challenge for us has been actually how do we make a robot compliant? Making a robot that's purely position control is relatively straightforward, but if we want to bring them into these real dynamic environments like the MIT Cheetah, it needs to be compliant. So how does one achieve compliance? There's, in robot design, there's Series Elastic, which is like the Baxter, and Rethink Robotics Sawyer. We have strain wave sensing, which is really cool, and that's the picture on the right. It's like, has a part count of like 4. It's awesome. But it requires these very costly transmissions that, this is actually a picture from Toyota, and Toyota has actually built this, and they believe they can't make this for cheap enough to actually make this scalable. So even Toyota is looking for other options that avoids that. So there's complexity in sensing and then the transmissions there. And then another way of achieving compliance is through quasi-direct drive. Now, the torque density isn't as good as others because you have a low gear ratio, but it's a really low part count. So all it is a motor, one small transmission, and an output. You get to even remove a part from what that beautiful thing is. So we decided to go with Quasi-Direct drive, and that was really trying to take the ideas developed at MIT for the MIT Cheetah and then apply them to robotic manipulators. So this is just one of their legs, and that gives you a feeling for what Quasi-Direct drive allows you to do, which is render a whole range of dynamics so that at any given moment, as a control engineer, you can select what kind of dynamics you actually want your manipulator to have, which is awesome for opening up a whole realm of new control opportunities. So our goal was to take that and turn that into a 7 degree of freedom manipulator, which ultimately led to 2 years of development and to the Berkeley Open Robot, which is where we are now. So we took some of these videos for ICRA that no one else has seen yet. And here we have a demonstration of the robot's compliance. It's in gravity compensation, and there's no special torque sensors. There's no series elastic here. It's just sensing motor currents, and yet it's still capable of this very compliant control. So here Steve is starting to actually mess with it. And this is what we mean by real-world dynamic environments. This is one quick example. Traditional robots like a UR5 would sense that impact, and then it would have to stop because it doesn't have the force sensing capable to so dynamically respond to an external disturbance. So let's see, I've got a few more interesting videos to really try and just like talk about and showcase the platform that we've developed. So here we had made coffee. This is all under teleoperation from these tasks forward. But the robot spilled, and here's I think what a great example of why you actually want a compliant robot is the robot has to actually clean a table. Now, if we asked a traditional robot to do that, if I were to teleoperate it, I would tell it to go an inch past the table, and it would attempt to smash right past the table and break itself, or if it was smart, it would turn itself off and be like, something is horribly wrong, please fix this. Whereas this robot can naturally just handle that because it's just applying a steady force downwards and is able to actually wipe down the counter. Wait, I can just skip the slide. So that was a little sneaky transition there. There was a minus sign at the what about Quasi-Direct's drive? It doesn't have great torque density. And that's a problem that we had to overcome. And because the main problem is with normal motors and gearboxes, that mass has to go at each joint. So if we wanted to roll here, you would need a motor and gearbox here. And if you wanted to pitch, like a wrist pitch, that would have to go here. What we were able to do is shift all of this motor mass back to right here and drive each joint through a differential. Now, what that means is, yes, our torque density is low, but the effect of gravity is very significantly reduced, and our inertia also drops off. And so for ICRA, our paper was entirely traditional control bandwidth tests, and the inertia of our robot is so low that we're able to actually move very quickly and be very dynamic. So let's see. Here's it holding, I think, a 5-pound weight, which is actually over our spec'd payload. And this is all in teleoperation. What I love about this is this showcases the robot's actually able to move and manipulate a certain payload, and then at some point I actually drop it because I don't actually succeed at the handoff that well, and it was fine. Now if you did that with any other robot, you might have dented something or had a huge impact force on the gearbox, but because we're Quasi-Direct drive, it moved it out of the way, but we kept running tests for the rest of the day. So one last, we had to do a towel folding video because that's the basis of our lab, but this one was just in teleop. And again, trying to find these pick points right on the table is I'm controlling this by looking at it like 15 feet away because we don't have great vision yet. And if I had a traditional robot, I would have commanded that thing past the table like every single time. Yet because this robot is force controlled, it was able to just touch the table, pick up the towel, and do it. We're trying to humanize the robot here. So our overall goal is to make this robot cheap. And for our prototypes, our rough cost breakdowns resulted in us being right at around our $3,000 bill of materials. But all of this is pretty much prototype costs in quantity one. And so we believe that given a really large scale manufacturing effort, we can bring this cost to around the $1,000 mark, if not less. Now, that's going to require significant demand, manufacturing work, supply chain work, and demand. So there's a lot left in the game, but we believe that with this paradigm, the pathway is there. So what's next? We're looking for a manufacturing partner to help us actually build this thing. And we're also trying to look into new ways to advance whole arm compliant control. A lot of robotics has been focused on these purely position control manipulators, because that's where we've been for the past 30 years. And there's still a lot of use cases where if we just need to establish pick points for grasping, a purely position controlled manipulator is awesome for that. Now, if you want to start taking robots next to humans in these really complex dynamic environments, it becomes much more desirable to have a robot that's very nice and compliant when it's just moving about, doing gross movements, but right when it doesn't, it just needs to do fine manipulation, stiffen up. And so actually breaking that problem down and making it, there's a lot of research work to be done in the compliant control space. So we've looked at this top-down approach to how do we make lower cost robots? How do we make lower cost useful general purpose robots? And it's a very challenging problem. And we've spent 2 years working on the nitty-gritty of what this needs to be done. And this has really led to us thinking, what is the robot revolution really going to require? And the biggest and most important thing is a community effort on all fronts. So robotics requires hardware, control, and application software all working together. It's going to require that scalable low-cost hardware, that software, and also the big one is conscious direct funding if we want to make low-cost robots happen. And that's not just us thinking that. That's how Willow Garage started with the PR2. And Toyota, even now, TRI, they started to realize that the market on its own right now will not bear low-cost robots because there's applications for high-cost robots. Everyone's going to want to keep making high-cost robots. And they've realized that they, and ideally among with others, are going to need to fund low-cost robot efforts to make that, to actually bootstrap that, to get it to a certain point where then there's enough robots out there, that there's enough people developing with them that actually makes them useful, and then the return on investment actually starts kicking off. And so then finally, once that happens, economies of scale. That's how we make, a Subaru Outback like $20,000, $24,000 or something. Instead of like, if we were looking at that like a robot, that thing should cost like $200,000. So economies of scale. So lastly, this research has been, on that funding note, has been funded by the National Science Foundation, TRI, and also the Baker Foundation. And that's the project.